Hello, my name is Marco Vassena, and in this video I will present automatically eliminating speculative leaks from cryptographic code with Blade. This is joint work with my co-authors from UCSD. Implementing secure cryptographic algorithms is hard. The code must not only be functionally correct, memory safe, and efficient. It must also avoid divulging secrets indirectly through side channels like control flow, memory access patterns, or execution time. Cryptographic code that has these features is said to be constant time. Much recent work has focused on how to ensure implementations do not leak secrets, for example via type systems, verification techniques, and program transformations. Unfortunately, these efforts have been foiled by speculative execution. Recently discovered Spectre attacks have shown that even if secrets are closely controlled via guards and access checks, the processor can simply ignore these checks when executing speculatively. These in turn can be exploited by an attacker to leak secrets through the cache via cache timing measurements like flush and reload and prime and probe. In principle, memory fences block speculation and hence offer a way to recover the original security guarantees. In practice, however, fences pose a confounding dilemma. Programmers can restore security by conservatively inserting fences after every load, but then endure the huge performance costs. Alternatively, they can rely on heuristic approaches for inserting fences, but give up guarantees about the absence of side channels. Since missing even only one fence can allow an attacker to leak the whole process memory, secure runtime systems, in particular browsers like Chrome and Firefox, isolate secrets from untrusted code in different processes to avoid the risk altogether. In this paper, we introduce Blade, a new, fully automatic approach to provably and efficiently eliminate speculation-based leakage from constant-time cryptographic code. Blade is based on the key insight that to prevent leaking data via speculative execution, it is unnecessary to stop all speculation as done by traditional memory fences. Instead, it is sufficient to cut specific data flows from source expressions, which speculatively read secrets, to sink expressions, which leak them through the cache. To prevent leakage, we propose and formalize the semantics of an abstract primitive called protect. Crucially, and in contrast to a regular fence which stops all speculation, protect only stops speculation for a given variable. For example, protect ensures that the value of E is assigned to X only after E has been assigned its stable, non-speculative value. Blade inserts protect statements to eliminate speculation leaks. First, Blade identifies sources and sink expressions in a program. Then it detects data flows from sources to sink, and lastly it inserts protect statements to cut the source to sink data flows. The program on the right is now secure because the protect statement prevents any secret introduced by the source from reaching the sink. Blade tracks speculative data flows by means of a static type system that conservatively approximates the dynamic semantics of speculation. The type system types each expression as either transient if it can contain speculative secrets or stable if it cannot. The type system performs static taint tracking and treats transient expressions as tainted. The typing judgment for expressions simply propagates a transient taint, and the judgment for commands restricts the use of transient data to avoid leaks. Intuitively, programs that are well typed according to this type system are free of speculation leaks. The typing rule for source and sink expressions require the array and the index to be typed stable to avoid secret-dependent memory accesses. Since reading arrays out of bounds can transiently introduce secrets in the program, the rule types the result as transient. Similarly, to avoid secret-dependent branches, the type system simply disallows branching on transient data. Existing programs that are free of protect statements are likely insecure under speculation and will be rejected by our type system. Therefore, we present an algorithm that finds potential speculative leaks and automatically synthesizes a minimal number of protect statements to ensure that the program is speculatively constant time. Here, the code reads two values from array A, adds them, and index array B with the result. Like the Spectre gadget from before, this code contains a speculative execution vulnerability and is ill-typed because Z is typed transient instead of stable. To repair the program, we first build a diffuse graph whose nodes and directed edges capture the data dependencies between the expressions and variables of the program. For example, in the graph, the edge from x to x plus y indicates that x is used to compute x plus y. To track how transient values propagate in a diffuse graph, we extend the graph with a spatial source node T and sink node S. Node T represents the source of transient values of the program. Therefore, we connect it to all the nodes containing expressions that explicitly read memory and thus create transient values. Similarly, node S represents the sink of stable values of the program and draws all the values of the program that must be stable to avoid transient execution attacks. Therefore, we connect all expression uses array indices in the program to the node S. The fact that the graph contains a path from T to S indicates that transient data flows through data dependencies into what should be a stable index expression, and therefore the program may be leaky. In order to make the program safe, we need to cut the data flow between T and S by introducing protect statements. This problem is equivalent to the problem of finding a cut set, that is, a set of variables such that removing the variables from the graph eliminates all paths from T to S. Finally, to repair the program, we simply add a protect statement to each variable in the cut set. The program on the right is now secure, but it contains more protect statements than strictly needed. This is because the cut on the left is suboptimal. In contrast, the cut on the right is minimal because it requires only a single protect for variable z. This cut is preferable because it requires as few protect as needed and therefore allows more speculation safely. Luckily, the problem of finding a minimal cut set is a classic graph problem called min-cut-max-flow, for which efficient polynomial time algorithms exist. One of the goals of Blade is to enable source-level reasoning about the absence of speculation-based information leaks. This is crucial to let the source-level type system use control and data flow information to optimally prevent leaks. However, there is a mismatch between the high-level reasoning principles required to prove our type system sound and the effects of speculation, which manifest at the very low machine level. We reconcile the tension between high-level reasoning and low-level speculation by giving the first source-level semantics model of speculation in the form of a JIT-Step semantics for a high-level while language. In contrast to previous semantics for speculative execution, our processor abstract machine does not operate directly on fully compiled assembly programs. Instead, our processor progressively translates high-level commands into low-level instructions just in time. To this end, the processor maintains a stack of progressively flattened commands and a list of fetch instructions called reorder buffer, and converts individual commands into corresponding instructions in the first stage of the processor pipeline. The processor pipeline consists of three stages: fetch, execute, and retire. We do not fix the order in which instructions and their individual stages are executed. Instead, we let the attacker supply those decisions through a set of directives. For example, by supplying directive fetch true, the attacker instructs the processor to predict outcome true for the condition E and speculatively follow the then branch, which is pushed on top of the command stack. Then, the processor inserts in the reorder buffer a pending guard instruction, which stores the predicted outcome for the condition and the else branch together with a copy of the current command stack as a rollback stack to restart the execution in case of misprediction. We proved three formal results about our JIT semantics and Blade. First, we prove consistency. Intuitively, consistency ensures that programs running on our processor produce the same results with respect to the memory store and variables as if their commands were executed in order and without speculation. Secondly, we prove that our repair algorithm is correct and synthesizes well-typed programs. Lastly, we connect the type system to our JIT semantics by proving that well-typed constant-time programs are also speculative constant-time. This result extends the pre-existing guarantees about sequential constant-time execution of verified cryptographic code to our speculative execution model. In the rest of the talk, I'm going to briefly discuss our preliminary evaluation of Blade. Our protect primitive provides an abstract interface for fine-grained control of speculation. However, whether Protect can eliminate leaks with tolerable runtime overhead depends on its concrete implementation. Ideally, Protect is implemented in hardware and exposed as part of the processor instruction set. Unfortunately, existing processors provide only coarse-grained control over speculation through memory fence instructions. These, however, might change in the future. Recently proposed microprocessor designs, for example, provide new hardware mechanisms to control speculation, which suggests that Protect could be implemented efficiently in hardware in the future. Though we encourage hardware vendors to implement Protect in future processors, for backwards compatibility, we implement Protect in software via speculative load hardening. The software implementation of Protect applies speculative load hardening to array reads. Intuitively, we rewrite array reads by injecting artificial data dependencies between bounds check condition and the loaded address, thus transforming control flow dependencies into data flow dependencies. Concretely, we generate a bit mask consisting of all ones or zeros depending on the outcome of the bounds check, and mask off the target address with the bit mask. Importantly, this solution works under the assumption that the processor does not evaluate the conditional update speculatively. We can easily enforce that by compiling conditional updates to non-speculative instructions like cmove on x86. We have evaluated Blade on a large dataset of cryptographic WebAssembly code. The dataset consists of a verified implementation of the Signal protocol based on the ACL* cryptographic library and several verified implementations of cryptographic primitives in constant time WASM. The original implementations of these benchmarks are probably free from cache and timing side channels. However, those proofs consider only sequential execution model and therefore do not account for the speculative execution vulnerability addressed by Blade. Our preliminary results are encouraging. The analysis and repair time scales linearly with the code size, and the analysis completes fairly quickly. The runtime is less than 10 seconds even for large benchmarks. Across all benchmarks, we find that the number of protections inserted by Blade is 2 orders of magnitude lower than Clang, which applies speculative load hardening naively to all non-constant array reads. Finally, our findings show that programs repaired by Blade are 2 orders of magnitude faster than those repaired by Clang. In this video, I have presented Blade, a new fully automatic approach to provably and efficiently eliminate speculation-based leakage in unannotated cryptographic code. Blade statically detects data flows from transient sources to stable sinks and synthesizes a minimal number of speculative load hardening-based protect calls to eliminate potential leaks. Our preliminary evaluation shows that Blade inserts 2 orders of magnitude fewer protection than Clang, and that repaired programs incur minimal performance overhead. Thank you for watching.